If you need to test a capacitor like this or this, something you might find in a motor or an HID light fixture, and you happen to have one of these handy capacitor testers, it's a no-brainer. You just connect the meter across the capacitor, read the display. This one says 28.6 microfarads, which is about right for this 30 microfarad capacitor. So we know the capacitor is good. That's well within its tolerance. But if you don't happen to have one of these, but you do have a meter that'll measure AC amps and volts, you can measure this capacitor using a source of AC voltage. I use a transformer, which provides me a low voltage AC source, which is isolated, so it's safe to work with. This transformer puts out 18 volts AC or so, and it's good for about 4.5 amps, so it'll handle a pretty good sized capacitor. You would need a transformer that would be good for about an amp for every 100 microfarads or so if you were running at about 27 volts. If you were at a lower voltage, it would be less current. For smaller capacitors, say 100 microfarads or so or smaller, a doorbell transformer would work just fine for the application. I brought the output of the transformer out to these two leads. I have a power strip here that I can just turn the power on and off because we only want to apply power briefly. And that would be especially important if we were using like a motor starting capacitor, because we'd only want to have power applied to it momentarily. I come out of the transformer, I go through the ammeter to one side of the capacitor and return the other side of the capacitor back to the transformer. So we come out of the transformer, through the meter, through the capacitor, back to the transformer. Then I'll take a second meter configured to read AC voltage and connect that across the capacitor. Schematically, it looks like this. I have the transformer input, 120 volts AC at 60 Hertz. Frequency is important. Secondary of the transformer, anything from 12 volts AC up to 30 volts AC, so it's safe to work with and we're isolated. Through the ammeter, through the capacitor, back to the transformer, and then across the capacitor we have our voltmeter. Turn on the power just momentarily to get an ammeter and a voltmeter reading, turn the power back off, and then we plug the values into our formula. We have a constant, which is 2652 times the amperage divided by the voltage. The result of the formula gives you capacitance in microfarads. All very easy. So let's turn it on and do our math. Now this capacitor is small enough, the current is low enough, we can leave this on continuously. This meter is set up to read in milliamps. We've got about 225 milliamps, which would be 0.225 amps, and we're at 20.78 volts, about 20.8 volts. So we take our constant, 2652, multiply that times 0.225 amps, and divide that by the voltage, 20.8, and we get our answer of 28.68 microfarads, which is about what our electronic capacitor tester said that it was. That's all very easy. A few cautions about capacitors. This is an energy storage device, so when you go to remove it from whatever device you're bringing it out of, whether it's a light fixture or a motor or whatever, short across the two terminals, because this thing can hold a charge. It could be several hundred volts, so short across it so you don't get hurt if you touch the terminals. Usually that isn't a problem if the motor's in good shape. It will have discharged it. This came out of a lighting fixture, a metal halide fixture. It has a bleeder resistor wired across the terminals, but the resistor could have gone bad and there could be several hundred volts across there. So always short across the terminals to discharge it. As you noticed, I left this turned on. You would only want to turn it on for a second or two to take a reading, especially if you're dealing with a larger capacitor like a motor starting capacitor, because those are only meant to come into play for about a half second while the motor started. And even though we're operating at a lower voltage so that the current would be lower, it would be passing a lot of current through the capacitor right now. It could be several amps, and that would cause the capacitor to heat up. So you only want to turn this on momentarily, get your reading, shut it back off. That's a very simple thing to do. Now if the readings come out low, you know you have a bad capacitor. Plus or minus 10% is not a big deal. In the larger capacitors, like a motor starting capacitor, like you might have on a compressor or a pump, which are going to be 300 or 400 microfarads or more, the tolerances are much greater. It might be 20% give or take, which would be acceptable for that. But if the motor is unable to start and the capacitor reads a little low, you may need to replace it. But other than that, it's really pretty simple. Now, if you don't happen to have 2 meters, and I happen to have 2 here, and they wouldn't have to be matching by any means. If you didn't happen to have 2 meters, you can certainly do the test with just one. You would connect up your 1 meter as an ammeter, as I showed you initially. Turn it on, get your amperage reading, turn it back off, disconnect the meter from the circuit, and connect your power source directly across the capacitor, reconfigure your meter for voltage, and connect it as a voltmeter across the capacitor, turn the power supply back on again briefly to get a voltage reading, and then plug those values into the formula, and you're good to go. And for those of you in a location where the power supply is 50 Hertz, modify your formula and use the constant 3182. That accounts for the different impedance of the capacitor at the lower power line frequency.